Okay, so let's start then. So, 1 second. Okay, so we've been talking about connections on manifolds. So just to emphasize, uh, the manifold a priori is just any smooth manifold, and the connection doesn't come with any extra structure. It's just a map from chi-m cross chi-m to chi-m which satisfies these axioms. Yeah. And then what you show is that you can localize this. So the connection, the global connection induces a connection on any open set. And then you show that the value of the connection on a vector field Z, it depends only on the value of the vector X at Z. So if you look at nabla X at Z, this only depends on the value of X at Z. So in other words, you could replace X by any tangent vector V at P, and you can define nabla V of Z. Okay. And this fact allows us to define what's called covariant differentiation along a curve. So given an affine connection nabla on a smooth manifold M, we have a unique correspondence for each curve C, a smooth curve C and M, from called capital D sub dt, from vector fields along C to vector fields along C, which is called the covariant derivative along C, which satisfies linearity, Leibniz rule, and compatibility with the connection, in the sense that if your vector field along the curve is given by restricting a vector field on M to the curve, then its covariant derivative dv dt is the same as nabla sub c dot t of y, where c dot t is the tangent vector of the curve C at the point Ct. And this makes sense because, as I just said, the nabla, the connection applied to a vector field Y, it only depends on the value of the vector field X at the point. And so here you can put any tangent vector. So it makes sense to apply a tangent vector to a vector field Y using the connection. Okay. All right. So the proof of this proposition was essentially the fact that using the actions for the covariant derivative along a curve, we found an explicit formula for it in terms of the Christoffel symbols of the connection. And what we found is that so this allows us to define, we can use this formula to define the covariant derivative. And then you show that this, this shows the uniqueness of the covariant derivative if it exists. And this formula allows us to prove existence by defining the covariant derivative via this formula. And then you check that it satisfies the axioms. And so that will also tell you that it's independent of the chart xi that you use. Here we're using a chart to define the formula for the covariant derivative. But because it satisfies the axioms, if I use any other chart, say yi, and I have a similar formula using the Christoffel symbols with respect to the coordinate system yi, then these two will be equal because both of them satisfy the axioms for a connection. And we've proved for a covariant derivative. And we've proved uniqueness of the covariant derivative. So therefore, they have to be equal. Okay. So is this okay? Any questions? Okay. So then we talked about parallel vector fields. So a vector field is parallel along a curve C. A vector field along C is parallel if its covariant derivative is identically 0. And this allowed us to define what's called parallel transport. So what we found is if you pick any point CT naught on the curve C, and you look at the tangent space at the point C naught, then for any vector, any tangent vector at C naught, there exists a unique parallel vector field along C whose value at CT naught is equal to the given tangent vector at CT naught. Okay, so this existence and uniqueness comes from the fact that this equation for a vector field to be parallel, dv dt equal to 0, you can see from this formula in local coordinates, it's a linear equation. It's a linear system of ODEs. And so we know that linear systems of ODEs are defined for all time and the solutions are unique. So when the coefficients are continuous. And so that will give us the existence and uniqueness of parallel vector fields. You have to patch together solutions in charts, essentially. And so then what we found is, therefore, if I look at the map which sends parallel vector fields along C to the evaluation homomorphism, which sends a vector field V to the value of V at T naught. So that takes values in the tangent space at CT naught. Then this is a linear map, which is an isomorphism, right? It's one-to-one because of the uniqueness of a parallel vector field with a given initial condition. And it's onto because of the existence of a parallel vector field with a given initial condition. Okay, so this is where we were last time. Is this all right?
Yes.
Yes.
Okay. So we also saw last time that, let me go down, that, this defines for us a family of maps called the parallel transport maps along the curve from one tangent space to another tangent space. It gives us a means of a family of isomorphisms which identify different tangent spaces. So what you do is you look at the space of parallel vector fields along C. And then if I take 2 points on the curve, let's say the starting point CA and some other point CT, then I have these isomorphisms. The space P of parallel vector fields is isomorphic to the tangent space at CT, and it's also isomorphic to the tangent space at CA. So by composing one isomorphism with the inverse of the other, we get an isomorphism from the tangent space at CA to the tangent space at CT, right? And this isomorphism is called, we're calling it P sub T. This is the parallel transport along C. So, so this is a one parameter family of isomorphisms, okay? And so maybe I should just say, right. So, I mean, the covariant derivative gives rise to this family of parallel transport isomorphisms. And conversely, if you're given this family of isomorphisms, you can recover the covariant derivative. You get it essentially by differentiating the parallel transport isomorphisms in the sense that the covariant derivative of a vector field V, dv dt, let's say at the point A, how do you get that? Well, you look at V at a point T, so look at Vt, that's a tangent vector at Ct. Now you have this isomorphism Pt from the tangent space at Ca to the tangent space at Ct. You compose with the inverse of this. Okay, you apply the inverse of this parallel transport isomorphism. So that will take you back to a tangent vector at CA. So then you get a curve inside a fixed vector space, the tangent space at CA, and then you take its ordinary derivative at time A. Okay, so this will be DDS at S equal to A of PS inverse of VS, right? So we showed that this gives back the covariant derivative, okay? And also it should be clear that if how do you get, I mean, these parallel transport isomorphisms defined for you, you can use them to define parallel vector fields, right? Almost by definition, if PT from T, let's say C0 to TCTM is your parallel transport isomorphism. And if V is any tangent vector at C0, then you can define the unique parallel vector field whose initial condition is V by putting capital V of T to be just PT of V. Okay, so this is the unique parallel vector field along C such that V0 is equal to V. Okay, so note the P0, the initial parallel transport isomorphism, is just the identity of the tangent space at C0. So is this clear? Okay. So one picture we used last time is, if I start with a basis at, let's say, the starting point of the curve, a basis for the tangent space, E1 up to En, little e1 up to little en, then you let capital EI's be the unique parallel vector fields along the curve whose initial value at time 0 is equal to little ei. And then you know that since the parallel transport maps are isomorphisms, for every t, capital E1 of t up to capital En of t will be a basis of the tangent space at CT. Okay, so this basis for each point of the curve, this is called a frame along the curve. Okay, and it's convenient to write vector fields in terms of such a parallel frame, right? That's what we did last time when we proved that the covariant derivative can be obtained by differentiating the parallel transport. Okay. So right now we don't have any other structure on our manifold. It's just a smooth manifold. So today we're going to talk about what happens when you have a Riemannian metric on your manifold. So what happens for a Riemannian manifold? So then we'll see that there is a unique connection which has some nice properties. In particular, it is in a sense compatible with the metric. So let's start talking about that. So such connections will be called Riemannian or Levi-Civita connections. So here's the definition. So let M be a Riemannian manifold. So I'm writing the metric as just inner product, okay? This is the Riemannian metric on my Riemannian manifold. So we say that an affine connection is compatible with the metric if for any smooth curve C in M and any pair of parallel vector fields along C, the inner product between these two parallel vector fields, say P1 and P2, is constant. Okay. So then we'll say the connection is compatible. So in this picture, if I start out with, let's say, an orthonormal basis of the tangent space, now the tangent space is an inner product space, then if my connection is compatible with the metric, then these EIs, because they're parallel, by definition, their inner products will be constant. And so that means that the capital EI of T will also be an orthonormal basis at each point, CT. Right? So this is what some of you were saying last time, that the EIs will be an orthonormal basis along the curve. So that's true if the connection is compatible with the metric, all right, by definition. So is this clear up to here?
Yes.
Yes? Okay. So we'll now find some equivalent criterion for the connection to be compatible with the metric. So the first proposition is that the connection is compatible with the metric if and only if for all vector fields VW along C, we have the Leibniz rule. So ddt of the inner product VW. So this is a function of T in the interval of definition of the curve C. So ddt of inner product VW should be inner product of capital dV dt with W plus inner product of V with capital dW dt. Right. So let's quickly prove this. So Nabla compatible with the metric if and only if ddt of inner product VW is equal to inner product dV dt W plus inner product V dW dt. Okay, so proof one direction is easy. So if you're given this Leibniz rule, then if you have two parallel vector fields, suppose VW are parallel along C. So that means that dV dt and dW dt are identically 0. And that implies, by our hypothesis, that ddt of the inner product VW This is inner product dv dt w plus inner product v dw dt. So that becomes the inner product of 0 with w plus the inner product of v with 0, because these are parallel, and so this is 0. And so inner product VW is constant. Okay, so one direction is easy. Is this fine? Yes?
Yes.
Okay. And for the other direction, we can use a frame along the curve, a parallel, an orthonormal frame. So, I mean, like I said, if you're given a compatible, a metric compatible connection, then if you start with an orthonormal basis, you'll get an orthonormal basis, right? So let E1 to En. So we're given, okay, so let me just write it this way. So let EI be an orthonormal basis of, let's say, TCAM, and let EI be parallel along C, such that EI of A is equal to little ei. I goes from 1 to n. Then nabla compatible with the metric implies that EI of T is an orthonormal basis of the tangent space at CT for all T. Okay. So now, given VW vector fields, along C, you let V be, say, summation AI EI. So because the EIs are a basis, we can write at each point along the curve V of T as a linear combination, summation AI of T, EI of T, where AIs are functions on the interval of definition of the curve C. And similarly, W is summation BI of BI EI. Okay. So then DDT of inner product VW. So because the EIs are an orthonormal basis, the inner product between V and W will be just summation AI BI, right? So this will become summation ddt of summation ai bi. So this will be summation ai prime bi plus ai bi prime. And so the first sum I can write as the inner product of the sum over I ai prime ei with the sum over I bi ei, right? And the second term I can write as the sum inner product of the sum over I ai ei with the sum over I bi prime ei. Okay. And the first term you recognize this summation ai prime ei, because the ei's are parallel by the Leibniz rule for covariant derivative of a curve along a curve. What is dv dt? dv dt will be just summation ai prime ei, right? By the Leibniz rule, because dei dt is 0. So this summation ai prime ei, this is nothing but dv dt, and this summation bi ei is just w. And similarly, this term here will be v, and this will be dw dt. So we get what we want. This is equal to inner product dv dt w plus inner product v dw dt. Is this clear? Okay, so this is because dv dt is equal to sum over I ai prime ei plus ai dei dt, and dei dt is 0, so this is just summation ai prime ei. Okay, similarly dw dt is summation bi prime ei. Okay, so when you write a vector field with respect to a parallel frame, in order to take its covariant derivative, all you have to do is differentiate the coefficients. All right. Is this clear?
Yes. Sir,
Okay. Yes, go ahead.
so AI is has to be differentiable, right? I mean, how do I get that? I mean, just take v inner product EI like that.
Yes. So the EIs are smooth vector fields, and so the inner product between V and EI is a smooth function, right?
Yeah, that's fine.
Yeah.
But last time, but the last time we did EI were not necessarily orthonormal basis, right? How do I justify there that AI is those coefficients were smooth?
Okay. So there, you can write it in coordinates. So
So if I'm there applying Gram-Schmidt, since like Gram-Schmidt's response process
well, you don't want to apply Gram-Schmidt because you don't have a Riemannian metric. What Orkojit is asking, for a general manifold, you don't have a metric.
Sir, hello.
So yes.
Just apply the change of basis formula. It will be I mean, smooth functions on which the
Right,
the
yeah,
matrix
so I
will
mean,
be
right, so EI you can write as some summation, say alpha ij del del xj,
Okay.
right? And this matrix alpha
Mhm.
ij, this
Is
will
a
be a
continuous.
matrix value of function of t. So this will
And
be,
this is smooth.
this is smooth. This will be a smooth map into GLN.
Mhm. Yeah, fine. Yeah, no, it's fine.
And now you just rewrite the del del xi's in terms of the EIs.
Mhm. Okay. Fine. Yeah.
Yeah, that's.
Yes.
This is smooth because the EIs are smooth. So therefore
Mhm.
this will be smooth. Okay. So now let's come to another characterization of compatible metrics. So as a corollary, we get that nabla is compatible with the metric. So in terms of vector fields on M instead of curves, nabla is compatible if and only if for all vector fields x, y, z on M, we have this Leibniz rule. This is what we saw for the induced connection on a submanifold of Rn, right? With the induced Riemannian metric, we saw that it satisfied this Leibniz rule. So the vector field x applied to the function inner product yz is equal to inner product nabla x y with z plus inner product y with nabla x z, right? So one direction is easy. So we have this corollary. Nabla is metric compatible if and only if x applied to inner product yz is equal to nabla x y z plus inner product y nabla x z. Okay. So one direction is easy. If the metric is compatible, then you let C be an integral curve of x. So let's stop this meeting now because the time is almost up. So 1 second, I'll just write here for all x, y, z in chi m. Okay, so let's stop now and we'll rejoin and I'll do the proof then.